Okay. Hello, everyone. I lost my plan. Sorry. This week, of course, we didn't have any Monday classes, but I have done something on today's classes. But from the past week, I have also something that I didn't do. So as a result, I'm going to also do it in here. But let me summarize one thing that we have said in the past week. There's a very special situation when the group is a finite group. Its representation theory is actually has some simplifying features. And this is what we are going to do in this semester, basically. We are not going to deal with any infinite groups or continuous groups. We will just concentrate on finite symmetric groups. So these are like groups of molecules, for example, right? If the group is a finite group, then we can say something about the representation. So one of the things is that every representation is equivalent to a unitary representation. This is something that I have done in the past week. Right? Every representation is equivalent to. So therefore, I can actually take all the representations to be unitary. So that's one of the things. And from now on, I'm going to assume that the groups are finite groups and the representations are always unitary representations. Because this is also what we meet in quantum mechanics. Naturally, all the representations are unitary representations. And the second feature is that if the group is a finite group, then reducible means completely reducible. So in terms of matrices, let's just remember what reducible means. I mean, reducible means that you can actually by a similarity transformation, you can convert a representation to a form like that, where we have like blocks like that in here, where we have a zero block in here. So we have diagonal square blocks, and there are these upper blocks which are also non-zero as well, but you can make this lower block to be equal to zero. Okay. But this is not what we want to do. We would like to make all the off-diagonal blocks to be zero. So you, as a result, want a representation where, well, when it is completely reducible, you can make both of these sides to be equal to zero. Right. So as a result, you basically have a representation where we have only the diagonal blocks. So the advantage in here is that you can express the representation as a direct sum of smaller representations. So that's complete reducibility is a nice thing. It turns out that if the group is not a finite group, there are examples of representations which are reducible but not completely reducible. There are examples. However, if the group is finite, then reducible is the same thing as completely reducible, right? I'm going to show you how you can do this. But the nice thing in here is the second feature in here. If the group is a finite group, we have shown that representation is, whatever the representation is, it's an equivalent to a unitary representation. And for a unitary representation, we have a very nice feature in here. So the idea is something like that. This is true for whether the group is finite or infinite, right? So if U is a unitary representation of a group, it doesn't matter what the group is, right? As I said, I mean, it can be an infinite group as well. But it's a statement about the unitary representations. And if W is an invariant subspace, of this representation, then the conclusion is that W perp is also an invariant subspace. What's W perp? Yeah, let me write it down like that. What's W perp? So for a subspace W, let me try to draw it like that. W is a subspace. W perp is essentially, I don't know, this is just a three-dimensional example perhaps, is the set of vectors which are perpendicular to all vectors in W. So W perp, this is called the orthogonal complement. sorry, orthogonal complement of W. It's called an orthogonal complement of a subspace. It's basically the set of vectors which are perpendicular to all vectors in W, all right? I can actually use the set constructed notation. It's the set of vectors where v dot W is equal to 0 for all vectors W in that subspace, right? You can actually think of it like that. So I think the best example is something like this. So if you just consider this three-dimensional space, right? If W is the XY plane, then W perp is the Z-axis. Okay, so in that case, dimension of W is equal to 2. This is a two-dimensional plane. The dimension of W perp is equal to 1. So it turns out that the sum of these two dimensions is equal to the dimension of the full space, for example, right? So in that case, let me use a color like that, right? So this W is this space, that W perp is this time is this one-dimensional. Okay. In any case, so it's basically the set of vectors which are perpendicular to W. These are complementary. You can actually show that the orthogonal complement of W perp is the W. So these actually complete each other in a way. Okay, so that's it's actually some geometric construct. So in any case, this theorem says that if the representation is unitary, and if there's some kind of an invariant subspace, then the orthogonal complement of the subspace is also an invariant subspace, right? So in any case, why this is so? Because I can actually do it like that. So I'm going to give this as an example. So this space might be like, the full space is bigger than 3 dimensions. This might also be big, as a dimension bigger than 3, right? Whatever, right? So let's say that this is W and this is W prime, W perp, right? So suppose that I have a vector in here, and I'm going to call this vector as, I don't know, let's call this as A, and I choose a vector in the W perp as B, right? So A is in W, and let's say B is in W perp. Okay, but the transformation is basically for a group element, let's say F in here, the transformation is basically transforms this vector to another vector, which is obtained by applying this matrix to the vector A, and similarly for B. Right? B is transformed into B prime, which is U applied on B. Okay. So the idea in here is this. Well, I think I'm going to use this quantum mechanical bracket notation. So the idea is that the unitary transformations are inner product preserving. UF is inner product preserving. Okay. So in any case, so since I have chosen A and B to be in these two subspaces, this is equal to 0, which implies that the transformed vectors are also equal to has a dot product which is equal to 0 as well, right? So let me kind of show it like that with a different color. So A is transformed into A prime, which is still in W, and in that case, B is transformed into B prime, right? B prime is also probably a different vector, but since the original vectors are perpendicular to each other, the transformed vectors are also perpendicular to each other. So it appears that since A prime is always inside the subspace, B prime should always be perpendicular to that subspace. So therefore, B prime is in W perp as well, right? You can actually think of it like that, but there's actually a more formal proof, right? So let's say it like this: if B is in W perp, so this implies that B inner product with A, let's say. I don't know how to express this. Yeah, let's just forget about this vector notation, all right? If B is a vector in W perp, then that's equal to 0 for all A in W, okay? Obviously. In any case, we would like to see, we define B prime as UF applied on B, and as a result, we just choose A to be in W and then try to see if this inner product is equal to 0. So we can do it like that. So that's A dagger multiplied with B prime. If I express it in terms of matrices, B prime is equal to UF times B. But I can think of this as the U dagger, A dagger, B. So therefore, that's the inner product of U dagger in applied on A, inner product with B. But U dagger is just the inverse of this. This is UF, right? Inverse of U, and it's actually a representation matrix of the inverse of the group element. Okay, whatever, that's basically inside W, but B is actually claimed to be equal perpendicular to all vectors in W, so therefore this is equal to 0. This shows that when I take an arbitrary element of W, A inner product with B prime is always equal to 0. This implies, therefore, that the B prime is in W perp, right? This is a more formal proof. In any case, so what's the advantage in here? If that's the case, that's what we are going to do. So we choose a basis for these two subspaces, actually. So let's say it like this. I'm going to do it like that, right? So that's an M orthonormal basis. Let's say A1, AM for W, right? Orthonormal means that each one is normalized. The norm is equal to 1. And any two of them are perpendicular to each other. Right? I dot AJ is equal to 0 if I is different than J. Now, I can also choose a set of an orthonormal basis for W perp, but I'm going to start the counting from M. So I'm going to call the first vector as AM plus 1, and so on. And let's say that AM is the last vector. Okay, so that's an orthonormal basis for W perp. But since these two subspaces are perpendicular to each other, these are also perpendicular to each other. So this implies that A1 to AM, AM plus 1, and so on, AM is an orthonormal basis for the full space. Okay. In any case, this is the one that we are going to use to do the similarity transformation. So the nice thing is that this orthonormal basis has, I can use this orthonormal, part of this orthonormal basis for spanning one of the subspaces and the other part for spanning the other subspace, right? So if I do this, I don't know, I mean, let's say it like this: UF applied on AI is equal to sum over, I don't know, some type of W matrix is going to be in here, AJ, right? There's going to be a sum, but depending on whether I is between inside this first M indices or the last of N minus M indices, we are going to have some of these coefficients to be equal to 0. Okay. So it turns out that since the W is invariant, sorry, yeah, this the name is actually is a poor choice. So let me call this as I don't know, ZF, let's say. So I'm going to write ZF in here. So since W is invariant, for the first n columns, we will have a structure like that. So there are zeros in here. So I'm going to do this as if m is equal to 4, right? And so 0, 0, 0, 0, 0, 0 in here. Okay. And this is basically when the index I is between 1 and m. In that case, only the first m coefficients would be non-zero. So each of these columns are actually these coefficients for a given I, actually. In any case, for the other ones, I'm going to have zeros in this part of the columns and non-zero entries in here. Yeah, whatever. I mean, at this point, we say that, well, if it is completely, well, in that case, this is completely reducible, basically. Okay. So this tells you that if a representation is unitary and is reducible, it's completely reducible, because if you do this trick, you're going to make this part of this matrix to be 0, that part of the matrix to be 0 too. And so as a result, this is just a direct sum of these two diagonal parts. Okay, so the idea in here is this, basically. This says that if U is a unitary representation and U is reducible, then U is completely reducible. Okay, so if I express it in terms of the subspaces, it kind of tells you this. If W is an invariant subspace, then U is reducible. In that matrix, you can only make the lower block to be equal to 0. But once you find this other invariant subspace, you also make the upper subblock to be equal to 0 as well. So there's actually some kind of a nice relationship between this subspace picture and the matrix picture. But I'm going to keep it short, so let's just come back to the original thing. So we're not really showing this. We are showing that for unitary representations, if they are reducible, they are completely reducible. So for unitary representations, this is always true. But if group is a finite group, then I know that every representation is equivalent to a unitary representation. And so therefore, if that representation is reducible, since the equivalence representation is also reducible, we have complete reducibility. So this then tells us that for finite groups, whatever the representation is, if it's reducible, then it's completely reducible. All right, that's essentially the idea in here. So therefore, for finite groups, we have like two different kinds of representations. We have irreducible representations where we cannot find any invariant subspaces. These are essentially our building blocks, right? So these are the smallest possible representations that we are going to have. Or we can have a representation which is reducible. If it's reducible, then it's the direct sum of some irreducible representations. So our job in group theory is basically for a given representation, try to understand if it is reducible or not. If it is reducible, then do the reduction and then do it as a direct sum of, express it as a direct sum of irreducible representation. So this kind of involves finding new bases and doing similarity transformations so that your reducible matrix representation basically is in this block diagonal form, right? So that's the idea. Perhaps I have explained it in a complicated manner as well, but I'm just going to give this example. So the group is, this is an example that we actually use a lot because the permutations of three objects, the group S3 objects. Just keep in mind that this is actually isomorphic to the group D3, which is the symmetric group of the triangle in the two-dimensional plane. But here I'm going to think of it as the set of permutations of three objects, right? So this is the smallest non-abelian group. It has 6 elements. These elements are not commutative, all right? And so as a result, it's kind of the best example for non-abelian symmetric groups and their representations, because it's the simplest such group. Okay, in any case, we have a nice representation in here. So from this group to 3 by 3 matrices, I can express P as the corresponding permutation matrices. So PF is the permutation matrix for F. So let's say, I don't know. I mean, in that case, we just think of this like it's a permutation of standard basis vectors, if you remember. E1, E2, and E3. Okay, so just a few examples. So P12, for example, or let's say P23, right? So this is just a permutation of second and the third basis vectors. So E1 is going to be left invariant. So the first column is E1. Second column will be E3 because the second vector is sent into the third vector. And finally, the third column is E2, right? So that's P23, for example. If I write P123, that's going to be like this. 1 is sent into 2, 2 is sent into 3, and 3 is sent into 1, right? So that's that permutation matrix. In any case, so this P from S3 to, yeah, whatever, 3 by 3 matrices is a representation of the group. Okay, so that's the first fact, right? Why? Because naturally you think that if F and G are two representations, PG multiplied with PF is essentially PFG, right? For any F and G is in S3. So this is naturally so because I can actually imagine S3 as the group as this matrix group, because I mean, these matrices actually do the same thing for these three objects, standard basis vectors, that an abstract set functions do, right? So as a result, it's quite natural to see that this is satisfied. So therefore, this is a representation. Okay. Second thing is that, well, this is the second thing. P is a unitary representation. Let's say that because it is non-preserving. So there are ways of actually seeing why this is unitary, because it's non-preserving. But so the idea in here is this. So P applied on a vector is actually a different vector perhaps, but these coefficients are actually exchanged, right? So I don't know, I mean, perhaps the first entry goes into the place of the second one and so on, whatever. But it is obvious that these two vectors have the same norm. So therefore, this is a non-preserving transformation. So that's PF, sorry. It's a non-preserving transformation. And so therefore, well, it has to be unitary. So PF is unitary. Right, it is actually, I mean, these are actually orthogonal matrices. You can actually call it as an orthogonal representation, but since the unitarity is the main idea, I'm just going to state that this is unitary. So all the matrices that are going to appear in here are going to be real matrices. So I could have equivalently used the orthogonal title, but since we are talking about the unitarity, let's just say that, I mean, let's just use the word unitary, right? So basically, orthogonal is a unitary matrix with real entries. That's it. Number 3. What was number 3? I forgot. So P has a natural invariant subspace. As an invariant subspace, right? Which is quite natural to see. If I have a vector where all entries are equal to each other, no matter how do I permute these entries, I get the same vector actually. So that's actually quite natural. So this is an invariant subspace that can be seen easily. So W is a subspace. So I'm not talking about a vector. The vector itself is invariant too. That's not really the important point. The important point is that every vector in that subspace is sent to another vector in that subspace, even though this other vector is still the same. So W is the space spanned by the vector 1, 1, 1. Okay, I don't know. I mean, people just write this as like the span, the linear span of 1, 1, 1, right? This is what the mathematicians do. But this is actually a one-dimensional subspace. Dimension is equal to 1. So since P is unitary and it has an invariant subspace, we can easily see that the orthogonal complement is also, so W perp is also an invariant subspace. Okay, so let's remember what W perp is. Basically, these are the set of vectors C1, C2, C3, where the sum of these these three coefficients is equal to 0. Because that's basically the dot product of this vector with that vector. I'm basically multiplying the corresponding components. And if it's 0, then yeah, you get this. Okay. So you can think of this as the linear span of, just take two vectors that satisfy this condition. So it can be something like that, right? So it can be a complicated vector as well, like 2, 3, minus 5 in here. It doesn't matter. As long as these two vectors are linearly independent, it's kind of obvious that their linear span is two-dimensional. And so as a result, it's a two-dimensional subspace. So that's something that we can write down. So I can express any vector like, I don't know, 1, 0, minus 1, for example, as a linear combination of these two vectors, right? But there are some coefficients in here. C1, let's say, I don't know. Let's call this like D1, and then this is D2 times 2, 3, minus 5. Whatever, I mean, or you can choose this and that as the basis, or I don't know, just choose two vectors which are perpendicular to each other. And I mean, there are various choices. When we do a similarity transformation, it is natural to choose an orthogonal basis for the space, right? In that case, I'm going to choose the second one in a careful way, right? But let's just note this. So in that case, for example, I don't know, let's say that we just take this permutation P12 and apply it to the second vector in here, let's say. So in that case, what I'm doing is like just changing these two entries in here. Want to change this, that. So I get this entry. This is a vector which is actually in this subspace, and it also has an expansion in terms of these two vectors, basically. So as a result, P12 within that subspace is going to have some different matrix representation. Okay? So, but the matrix representation depends on which basis I choose in here. Okay, so as a result, we have found two subspaces. Okay? So the trick in here is to find, well, let's say it like this, find a new basis. A basis, since this is a three-dimensional subspace, sorry, it's a three-dimensional space. The full space is three-dimensional. The 3 by 3 matrix representation. So I'm going to find a new basis such that the A1 spans W and A2 and A3 spans W perp. And if I express the my transformations in here, in this new basis, then I'm going to get a representation which is already in block diagonal. But I don't stop here. I also assume that A1, A2, A3 is an orthonormal basis. I can do that because W and W perp are perpendicular to each other. So it's natural that A1 is perpendicular to both A2 and A3. So as a result, if I choose A2 and A3 to be perpendicular to each other, then these three vectors would be automatically perpendicular to each other. Okay, so I can do that. What's the advantage in here? So in that case, let's say it like this, V, so that's the basis change matrix from the standard basis to A1, A2, A3 is a unitary matrix. Why? Because that's a property of the unitary matrices. So they actually transform an orthonormal basis to another orthonormal basis, because unitary matrices actually are norm preserving. So therefore, E1, which is a normalized vector, unit vector, is transformed into a unit vector. And unitary transformations are angle preserving. Well, these are, I'm saying unitary, but this is actually an orthogonal matrix because all entries are real. So since E1 and E2 are perpendicular to each other, this basically transforms perpendicular vectors to perpendicular vectors. In any case, so since the basis change matrix is the similarity transformation matrix, I mean, it's the matrix that we are going to use in the similarity transformation. So therefore, this is actually a unitary similarity transformation. So let's say it like this. So from these permutation matrices, we are going to pass to new matrices. So I'm going to express them like that. The new matrices are actually obtained as a similarity transformation of old matrices. But these are unitary, right? So therefore, this is like, for example, this is equal to V dagger. So let's write it down like that. V dagger PFB. And the PF is already unitary. So therefore, this is also unitary. Okay. Meaning that, well, if I do a similarity transformation where the basis change is a basis change from an orthonormal basis to another orthonormal basis, in that case, this is a unitary similarity transform, which transforms unitary matrices to unitary matrices. It's kind of confusing, actually. This is a unitary similarity transform. And if PF is unitary, then I also convert these to unitary matrices. That's, I think, one of the important things in here. So if we just keep using unitary representations for finite groups, then this kind of a diagonalization or block diagonalization is not going to change the nature of the unitarity of the representation. So you basically do a similarity transformation from a unitary representation to another unitary representation, because your similarity transformation is also unitary. All right. In any case, so that's what I'm going to do in here. So that's numbers 5. So I'm going to choose A1 as the vector 1, 1, 1 because I require that this span W. Obviously, this is so. I just need to normalize this. So as a result, I divide by √3. For the second vector, I can choose any vector where the sum of the coefficients is equal to 0. So in that case, this is equal. I'm going to choose it like that. So that's going to be, with normalization, it's going to look like that. And the third vector, so there are some practical ways of finding this third vector, but let's just keep in mind that this vector has to be perpendicular to these two vectors and has to have a unit length. So you can use, for example, the cross product of these two vectors to define this one in 3 dimensions. In higher dimensions, you have to use some other methods. So here, I'm just going to do a very simple reasoning here. So I know that this A3 has to be perpendicular to this one. So that means these two coefficients have to be the same. So I can really say that the first two coefficients are equal because this has to be perpendicular to that. Finally, this has to be perpendicular to the first vector. So that means the sum of the coefficients are equal to 0. So that means the last coefficient is equal to minus 2c. Right, and then do some kind of a normalization, whatever. But let me do it like that. So that means if I take C out, I get this matrix in here. But if I do the normalization, then I can see that this is 1/√6. Okay, so because of that, V is actually a matrix where the first column is the A1, second column is A2. Yeah, whatever. I mean, that part is not that important actually. Now, what I'm going to do is I'm going to compute QF, but I'm not going to use this matrix expression to find what that QF is. I'm just going to use the usual expansion. So the idea is something like that. If I apply PF to AI, I'm going to get a linear combination of all the other matrices in here. All the other unit vectors. By using this expansion, I'm going to find these coefficients. So these coefficients are actually the matrix elements of the final matrix that I'm going to obtain. All right. So this QF is that matrix. So what I'm going to do is I'm going to compute PF applied on A1. I'm going to get an expansion. So from here, I'm going to find the first column of, for example, QF. And so the first column is going to be determined like that. So, and then I'm going to find PF applied on A2. So that's going to give me the second column. And so on, right? PF applied on A3 is going to give me the third column. So let me, by undoing this, let me do this. So first of all, let's just do this calculation. But since A1 is just 1, 1, 1, for any permutation, this is going to be just A1. As a result, the first column is always 1, 0, 0. Whatever the permutation is, right? Because A1 is really invariant. Why this is 1, 0, 0? Because I'm writing down the coefficients in here of the expansion of that vector in the new basis. Okay. Now I'm going to do the same thing for A2, but this time I have some difficulty because the operation that I do is going to depend on what the permutation is. So let's suppose that I don't know, F be the permutation of let's say 1, 2, 3. I'm just using this example in here. So in that case, I'm going to compute the second column too. So I'm just going to think about what that particular representation does to A2. So let's remember this P1, 2, 3. I'm not going to write this in matrix form because I can do this calculation easily. Okay. So what happens is that this is a vector where first entry is replaced with the second. So the second entry is 1/√2. And the second entry is sent into the third one. So I get -1 in here and 0 in here. Okay. So this is a new vector. So I don't know what to call this. So let's just call this like, I don't know, A2 prime, for example, right? It's the A2 is transformed into that vector. Now this is A2 prime. And I would like to write this as a linear combination of these three vectors. So this is A2 and this is A3. I know that the first coefficient is equal to 0. I actually didn't need to write this thing down because I know that with a permutation, I'm going to get a vector in the W perp subspace. So therefore, this vector is just a linear combination of A2 and A3. Okay, so the first entry is not there. So that means this is going to be equal to 0. I need to find the second coefficient in here. Yeah, let's just first of all write this thing down like that, right? 1 over root. Yeah, let's just forget about it. So this is actually the problem of like finding two unknowns by using two equations. So it's actually a linear algebra problem, but there's a very nice simplifying feature in here. If I actually take this equation and multiply it with A2, take a dot product with A2, right? The whole equation. What happens is that, first let me write down the equation and then, right? Yeah, I mean, I have taken this equation and then taken the dot product of that equation with A2 from left, right? So here, since A2 and A3 are perpendicular to each other, this is equal to 0. And since this is normalized, this is equal to 1. So that means the right-hand side is equal to D2. So all I need to do is in here is compute D2. I need to compute this dot product. Okay, I don't need to solve anything. I just need to compute this dot product. So in this case, sorry about that. A2 prime is this vector. A2 is that vector. I have to somehow find the dot product of these two. So that's actually quite hard for me to do. So yeah, well, whatever. So I can kind of see that the dot product is -1/2, right? So that's -1/2. So D2 is -1/2. So in that case, I'm going to take this equation and this time take the dot product with A3. So it's the same equation, but this time I'm taking the dot product of each term with A3. And on the right-hand side, again, there's a simplifying feature. So that dot product is equal to 0. That's equal to 1. So I get the coefficient D3 in here. So I need to take the dot product of this thing with A3. This is also a little bit more tricky. So this is my vector, and A3 is this one. This one in here. All right, how do I see? Okay. So the second minus the third. Second minus the third, so that's 3 divided by √12. 3 divided by √12. √12 is 2 √3, so that means this is √3/2. Okay, so that means this entry is equal to -1/2. That's equal to √3/2. Let me quickly do the second calculation. Right, the last calculation actually. So P123 applied on A3. A3 was 1/6, 1 minus 2, right? Sorry about that. I need to get back this. I think I'm going to do something like that. I'm going to copy this. All right. And paste somewhere in here. Oh, sorry. I made a mistake, right? All right. And then I paste somewhere in here. Let me erase this. All right. Let me box this. All right. Yeah, I don't know. Okay, so P123. So 1 is replaced with 2, right? So these two are 1, and that's equal to -2, right? So that's my new vector. So let's just call this as A3 prime. So this A3 prime, I'm going to expand this in terms of the these things in here. So I'm just going to call the coefficients as like C2 times A2 plus C3 times A3. So C2 is equal to A2 dot product with A3 prime. And C3 is equal to A3 dot product with A3 prime. So let me quickly do these calculations. A2 dot product with A3 prime. All right, that's difficult. So 1 over root 12 is there. Minus 2, minus 1, minus 3 over root 12. Minus 3 over root 12. Again, so that's minus 3 over 2 root 3. So minus root 3 over 2. All right. And finally, A3 prime. So A3 is this, A3 prime is that. So again, there are minus signs somewhere. Right, I'm just going to magnify. All right. So we have like minus 2, 1, minus 2. So we get minus 3 divided by 6. Sorry, magnify again. So that's minus 1/2. Which means, going back to this coefficient is 0. That was minus 1/2. Sorry about that. I forgot about the other one. That's minus root 3 over 2. All right. Okay, so in any case, so what's important in here is that this is in block diagonal form. So we have a 1 by 1 block in here and a 2 by 2 block in here. Right? With special methods. How did we achieve this? Basically, this block corresponds to the transformation of vectors in the W subspace, which is one-dimensional subspace. W is a one-dimensional subspace. This block corresponds, well, tells us how the vectors transform in this W perp subspace, right? So each of these are invariant subspaces. So I can think of this PF transformation as a transformation in that particular subspace and the transformation in this perpendicular subspace, okay? So in this form, we are kind of seeing this in a clear way, actually, right? You can actually think of it like that. But our job is like, take a complicated initial representation, let's say. This representation is somehow depends on your problem, so it's defined by the problem actually. This representation can be reducible by choosing a suitable orthonormal basis. We would like to convert that representation to a block diagonal representation like that, right? That you can think of this as our job in group theory. As a result, I mean, this is essentially how we achieve it. However, in here we had some shortcuts in here. So, I mean, the P representation that we have started with had an invariant subspace. Somehow we were able to see that invariant subspace easily. If the group is complicated and the representation is complicated, it may not be easy to see such invariant subspaces. So as a result, we have to have some certain systematic ways of actually recognizing or finding these invariant subspaces, or finding whether a representation is reducible or not, right? So as a result, I mean, starting with the next week, we are going to see these. So we are going to see that there are like very nice tools that actually enables us to decide on these kind of things. Actually. Okay, let's finish it at this point, and let me stop the recording.